last video was about the limitations on the power you can dump into a end-fed half-wave with ferrite cores. And the limiting factor was the temperature that the ferrite core got to. And I ended that video rather abruptly because I suddenly realized there was another more important issue that we had to talk about first. There's a link to that video in the description below. But at any rate, we said that the max power was limited due to the heat in the core. And, well, what causes the heat? The losses in the core, of course, cause the heat, but what causes these losses? And it turns out it's a non-linearity known as hysteresis. And it's well known that non-linearities in transformers cause harmonics. The power company has considerable problems with harmonics, that is, currents in the lines that are at multiples of the main frequency, either 50 or 60 hertz, as the case may be. And they can tune power factor to unity at the fundamental frequency, but when there's harmonics, then all kinds of strange things happen, and there's losses in the overall power system. Now, if the same thing is going on with the auto transformer that's in our half-wave antenna, our end-fed antenna, is this antenna legal? Are we spewing out spurious emissions in multiples of the fundamental frequency? And I have a breadboard set up that I'll demonstrate this nonlinearity, and then we'll go out and transmit with the antenna that I showed you in the other video, and we'll listen on another receiver to the frequencies that are multiples of the frequency we're transmitting on, and see if we can find harmonics, and if so, measure them. Now, to understand the nonlinearity and the hysteresis, let's talk about a regular resistor here. We can show the current that we can put into a resistor and the resulting voltage in this way. If it's a 1 ohm resistor and we put 1 amp through it, we get 1 volt. Now, what if this resistor was not linear? What if we had a resistor that changed with current? Now it turns out we have to look at the slope of the line at any point to calculate the dynamic resistance at that point. And a similar thing is done with magnetic circuits. And to characterize a core, we use what's called a BH curve. This is B, which is flux density in the core, and this is H, and that's the magnetomotive force driving the flux in the core. So if we had a perfect inductor with a magnetic core, we would have a straight line. But that is not what we have. If you look at BH curves for magnetic materials, you'll see as we go up, it'll look like that. Now, this H here is amp turns per meter, and the meter is the mean length around the core. And the flux density has to do with the cross-sectional area of the core. So flux is actually given in Webers, and flux density is Webers per square meter. So that cross-section there would be a square. Now, as we slowly increase the current, we find we get less and less flux as we go up, or I should say flux density. Now if we reduce the current, turns out we don't come back down the same way we went up. And when the current's at zero here, we still have magnetic flux in the core. Now this is what happens when a screwdriver gets magnetized. It'll stay there even without any magnetizing force. And if we reverse our current, we start to come down, and it's symmetrical this way, but we don't go back up the same way that we did initially. So this is called initial permeability, and it turns out the losses in the core are proportional to this area. This is called a hysteresis loop, and the bigger the loop, the more losses you have. Now when we have very small signals, when we're operating down in this area, we have a very small area of hysteresis. So, but as we use more and more current and get a higher and higher flux density, these losses due to hysteresis grow very rapidly. So if you want to learn more about magnetic circuits and transformers, I have several videos listed below in the description covering magnetics and transformers, and several videos on how inductors work. So next we'll go to a breadboard, and I'll show you the result of this hysteresis in a non-linearity in a circuit. Here's our breadboard set up. I have some nails into a piece of wood to support some components here. This is a ferrite core. It's an FT82-43 with 50 turns of number 24 wire on it. And this here is a 47 ohm resistor. Now over here I have an oscillator, function generator, and an oscilloscope. And the output of the oscillator is connected right here, and the scope is also connected between those 2 points. So we're showing the output of the oscillator on the scope. And then I have a clip lead attached to that same point, and I'm going to attach this to the 47 ohm resistor while showing you the scope. And you can see the signal falls just about in half when I connect that resistor. Now the output impedance of this oscillator is 50 ohms, which is just like a amateur radio transmitter might have an output of 50 ohms. So when we load the output with 50 ohms, we divide the voltage between those two impedances. So the amplitude goes roughly in half. Now when I connect this choke that we made to the oscilloscope, you see again the amplitude goes about in half. Now that's because I picked a frequency where the impedance would be in half to make this demonstration. So now it doesn't look too bad. Here it's back in the circuit. There is some slight distortion here. You can see we've got a bulge here and a concave here compared to a very nice sine wave. Now I'm going to increase the amplitude. Right now our amplitude is 3 volts peak to peak, and I'm going to increase that. There's 4 volts peak to peak, 5 volts peak to peak, 6, 7, 8. So you can see distortion happening, and of course it gets worse with amplitude. Let me change the range of the scope here. There's 10 volts. Okay, there's 20 volts peak to peak applied to that inductor, and you can see the severe distortion of the waveform. Okay, now we've seen how a nonlinear magnetic material can distort a signal. And what does this actually do? Let's talk about spectrum for a minute. If this is the amplitude of a signal and this is frequency, a pure sine wave would look like that. It only has one frequency component, and that's called the fundamental. It's also referred to as the first harmonic. So if a signal has other harmonics in it, it's no longer a sine wave. And there's a branch of mathematics called Fourier analysis, where you can take any arbitrary waveform and determine the amplitudes of the higher harmonics. They can also be negative. You can add harmonics or subtract harmonics to come up with the waveform. Also, for a given waveform, if you know the spectrum and have at your disposal a bunch of oscillators that you can set at different frequencies, you can synthesize that waveform by adding up the harmonics beyond the fundamental and recreate the original signal. So the oscillator that I showed you earlier has two channels, and what I'm going to do next is combine those two channels and show you a waveform that we can create by adding those two channels. Okay, here's my oscillator / function generator, and you can see it has two output channels, and they're set at a frequency ratio of 3:1. Now I have both channels connected to our 50 ohm or 47 ohm resistor. Now each channel has a 50 ohm output, so we're actually summing the signals together at this node. And right now I have the amplitude of channel 2 set to 0. Now let's watch the waveform as I increase the amplitude of channel 2. Now we see distortion coming in. And you can see this looks vaguely familiar to the waveform I showed before from the distortion caused by the ferrite core. Now, of course, there's maybe more harmonics involved than just a third harmonic. So what we can do next is actually use our transmitted signal and try to find all the harmonics that might be in the transmitted signal. I don't have a spectrum analyzer, so all I can do is use a receiver and only look for several harmonics of the fundamental. The receiver that I was going to use for this experiment only goes to 30 megahertz, so I decided to set up my antenna so I could transmit on 40 meters or 7 megahertz. And that way I could look at 3 of the harmonics and be under the 30 megahertz frequency. So the way I got the antenna working on 40 meters was normally it's 32 feet high and just a vertical wire. So I added a sloper of 32 feet, and that got me on 40 meters. And it turns out when you do this, you also can get on 15 meters. So I set this up as far away from the receiver as I could go, which was about 180 feet. And I used a very small antenna on the receiver, which turned out to be about a 4-inch vertical whip. So next I'll show you the results of that experiment. My setup for looking for harmonics generated by our antenna. And this is a Kenwood 570, and it's has a piece of coax connected to it, and the coax is just taped to this support stand here, and I'm using about a 4-inch alligator lead as the antenna. Okay, here we are on the fundamental frequency that I'm transmitting on, and signal is 10 dB over S9. Now let's go up to the second harmonic, which would be on 20 meters. And here we're hitting up to an S9. On the next transmission, we'll go up to 15 meters, which would be the third harmonic. Okay, and there we're hitting an S7. And then on the next transmission, we'll go up to 10 meters, which would be the fourth harmonic. And I don't find anything. So there's definitely signals on the second and third harmonic. Here are the measurements from my experiment. I found the fundamental frequency. I had a signal level of 10 dB over S9. The second harmonic I was measuring at S9, and the third harmonic I was measuring at S7. So just as the theory of distortion due to the magnetic flux says there should be harmonics, I did detect harmonics, and they were quite strong. So this is a rather crude setup. I really need someone with laboratory grade equipment to get involved with this. Another problem is, what are the conditions? What power level do you make these measurements at? What core temperature do you make these measurements at? This is really a messy area. So the FCC rules state that below 30 megahertz, power in a spurious emission signal must be 43 dB below the fundamental power. So I don't know if we're exceeding that or not in reality. Now, in the June 2023 issue of QST, on page 55, there's an article about a new committee that's formed that they call the Clean Signal Initiative. And they talk about this is the issue, and they talk about the ARRL labs working on projects to clean up. They mostly seem to be concerned about intermodulation, distortion, and splatter, but I think they'd be willing to investigate this area as well. So I plan to try and contact them and see if they could make some measurements and give us some real scientific information on this subject.